everyone. My name is Nicolas Rinaudo, and I'm here to talk to you about optics. And usually I like to start these things by explaining why I'm relevant to the subject at hand and why you should spend the next 40 minutes or so listening to me speak on that matter. It's a bit complicated for optics because, well, I'm the CTO of a company called Besedo. We do a lot of online content moderation, and we have a pretty solid Scala code base by now. Not one optic in there, not one easily lens, nothing. We don't use that yet in our production. I also maintain a couple of open source Scala libraries, the least obscure of which is probably CSV, which is 2 CSV white services to JSON, basically. Doesn't use optics at all either. Give a couple of talks at conferences and stuff like that. This is my only talk on optics, so I might be able to use that as reference after I've been here, but so far no actual concrete evidence on why I should be talking about optics. The reason for that, though, there's a good reason, is optics are extremely intimidating. I didn't want to learn them for the longest time because the vocabulary we use is really esoteric. Lenses, prisms, it sounds scary. I just didn't want to learn them. Then one day, decided everybody was telling me to learn them, Julien there, that I should learn them, they were really interesting. And I actually sat down, worked on them, and found out that when they're presented properly, when you learn about what they're meant for and not the theory behind it, beautiful as it may be, optics are really quite easy to get and really quite useful. So my goal in this talk tonight is not to make you optics experts, but to convince you that they're actually useful, actually interesting, they're within your grasp, and that you might want to try them out in your work starting tomorrow. So we are not going to be doing anything fancy. The only prerequisite that I have is that you understand basic Scala syntax. We shouldn't do anything too complicated. If in the code that I'm going to show you see anything that's not clear, do interrupt me. I like these talks a lot more when there's a communication with you guys, so please do not hesitate to interrupt if something doesn't make sense. One thing that would be useful is for all of you to have basic knowledge of what algebraic data types are, but even if you don't, I'm going to spend the next couple of slides giving a quick reintroduction to them. So that's it. I don't actually know how much time I have because I was supposed to finish at 8, that's in 20 minutes. I have 111 slides, that's not going to work out. So do interrupt me when I run out of time. It can basically be interrupted at any point. Right, okay, so first, algebraic data types. Is anybody not familiar with the concept? Apparently nobody isn't familiar. I'm going to guess that's a lie. So let's explain them nevertheless. What's an algebraic data type? So algebraic data types have 2 main categories. One of them is product types, which product types are types that are composed of other types. So here, basically in Scala, your standard case class. Where here, our example classifier is classifier in the machine learning sense. So it's something that, given an input, classifies it and puts it in one of a number of classes. And we have defined it as described with the name, which is a string, and the number of classes that compose it. That's a product type. A product type is called product because the number of elements that compose it is a product of the... Does this have laser? Yeah, it does. Right. So the number of elements... Okay, it can does. Right. Number of elements that can be in ML service are... Yes, that's the wrong one. Sorry. Number of elements that in classifier are the product of the number of elements in string and the number of elements in ints, so name product. Then you have some types. Some types are kind of the same, but the dual. So instead of being a list of elements, it's one value outside of a list of elements, which in Scala we are going to model through this kind of messy construct. It's nothing fancy, it's just seal trait and implementations. And here I'm using the example of an authentication mechanism, which can be either a token, which is a string, so you just pass a token and you're going to be authenticated, or a case class, which is login, username and password. That's going to be a sum type. Sum type is for exactly the same reason that product type is called product type, it's called sum type, because the number of elements that can be part of auth are the number of values of token plus the number of values of login. And usually when we talk about ADTs, algebraic data types, what we mean is composition of some product types. So here, ML service is the composition, it's a product type of O, which is a subtype, and of classifier, which is a product type. So, and this is the example that we're going to be using for now. So, ML service is an authentication mechanism and a classifier. This is how you authenticate to a classifier and then run prediction models. And that was about all I had to say about algebraic data types. I'm not going to talk about the other one, exponential types, which are functions. Do we have any questions at this stage? Yes?
Is it some type code?
Yes, it is. But we call it subtypes here. But the same thing. I think there might be a slight difference with, for some types, the order of the types doesn't matter. But I'm not entirely sure. But they are definitely related. Right. Lenses. So when we write code, so we have an instance of ML service, which have an authentication mechanism which we don't really care about at the moment, and a classifier. And we want to change the name of the classifier from news20 to news_20. And if we wanted to do that in an imperative language, such as Java, for example, it'd be pretty straightforward. We just write that, and this is pretty explicit and short and terse, and it's quite nice. In Scala, not so much. And this is actually not the worst. I only have a depth of 2 from ADT. I started writing these slides in ADT with a depth of 3, but that wouldn't fit on the slide. So this gets really, really nasty really quickly. And surely we can do better. We like to say that when we write functional programs, that we can do the stuff that imperative language do, but without a lot of the boilerplate. Clearly here, the boilerplate is on our end. So we want to fix that. And so the first attempt that we are going to make is to create a generic setter type. I'm going to spend just a bit of time on that slide to explain the type parameters because they're important for the rest. So my setter type has 2 type parameters, S and A. Those might sound odd. Those are the traditional names for this type parameters that you'll find in the literature. So that's why I'm using them here. So when you read more on lenses and prisms and optics later, you will know what this refer to. S, I believe, stands for state. I've tried to look it up, to look up the origin. I discussed it with people. The consensus, it came from state, so that's why it's an S. I couldn't actually prove it. And this is a type of the object you want to modify, and A is just an A, and it's the type of the value you want to modify. So in our case, for example, we wanted to modify the name of a classifier within an ML service, so our state would be the ML service, and S would be ML service, and our A would be the string. And so the setter class here would just have this single method, which given an A and an S, would modify the A within the S and returns modified S. And it's carried because it allows for nice syntax, stuff like that. But this is a bit limited. Very often we like not to set a value, but to be given that value and to modify it. A bit like functional maps, for example. So if we had a modify method on top of set, we could do that. So let's write that, where modify takes a function from A to A, an S, and returns a modified S. And this is nice, but we could make it better, because if we had a get method that returns the A from within the S, so that returns the classifying name from within the ML service, we would be able to implement modify and provide it for free to have default implementation. So, so this is what we've done here. This code here is not extremely interesting. You don't have to read it and to try and understand it. All the code from these slides have been compiled while generating the slides, so all the code does work, does compile. You don't need to try and find mistakes. There cannot be any mistakes. There were many, but then I compiled it, and now they're not. And so at this stage, setter doesn't really seem like a great name for our type, because not only does it modify, but it gets. So a setter that has a get is a bit weird. So how do we call that? Well, it's a type that allows us to focus on a specific part of a product type. How could we call that? Well, a lens. Because it sounds nice and esoteric, and it's from another branch of science. We like to have these things. I'm personally not a very big fan of the names in optics. They scared me away from the thing for so long that I'm going to make fun of them a bit. But this is what a lens is. This is something that allows you to focus on a specific part of a product type and work with it. This looks a bit painful to instantiate, and we're going to be creating a lot of instances here. So let's write some creation helpers. There's nothing really fancy here. We have an apply method that takes both a setter, so that takes an A and an S and returns yes, and a getter that takes an A from an S, and we just stick them into a lens, and that gives us an implementation. But we are going to type alias a few of these because it's going to help us follow, to come up with some intuitions later. So this A to S, the A and S to S, we're going to call that a set SA, and this S to A, we're going to call that a get. Right, so set is given an A and an S, I set the A and the S, and get is given an S, I extract the A. If at some point I'm going too fast, or there's a lot of S's and A's in what I'm saying, so maybe you just need to slow down or ask questions, please do so. And so this is just the creation helpers rewritten with the type aliases. And now we're going to, now that we have everything we need, we have the lens, we have ways of creating them, so we are going to actually create them and use them to do what we set out to do, which was to modify the classifier name inside of an ML service. So let's create our two lenses. The first one, classifier lens, is a lens that allows us to go from an ML service to a classifier. The implementation is fairly straightforward. It looks very similar to the next one, which is a lens that allows us to go from a classifier to the name of the classifier, which is a string. Clearly, this code looks like it could be generatively, yes?
Quick question. If the field, classifier field, was an optional, your A would be an optional classifier, and then you have to deal with that?
I would prefer not to answer that now, because that would be telling, because we tackle that a bit later. But it's a very good question. I am not going to answer because I'm going to answer it in like 10, 15 slides. So yeah, so this code is, it looks very redundant. The first one and the second one are basically the same. Of course, it can be automatically generated. I'm going to be explaining how later. And now we use it to do what we want to do. So given a classifier lens and a name lens, we do the whole thing to set the name of the classifier. And it works exactly as we wanted. We do have an instance of ML service where the classifier name has been changed. And it's very disappointing, isn't it? It's not that much better than what we had at first, and it's clearly not as good as what we had at the very beginning with the imperative language. So this is not good enough yet. It's possibly some progress, but definitely not what we wanted to have. So let's try and make it better. And usually, when I have this kind of code that I want to clean up, the way I do it is I put everything into a function, put everything into parameters, and see whether I can come up with a generic pattern that will allow me to make it beautiful. So let's try to do that. Let's write this setName method, which takes our two lenses, so our lenses from the main service into classifier, and from classifier into a string, and that is basically the implementation of what we had before, just copy and paste with string names. But if you look at the implementation, nowhere in here do we need to know that this is an ML service, this is a classifier, and this is a string. We just need to know that the types match, but we don't need to know the actual types. So we could just make them type parameters. And this is the same method. And if you look at it, hopefully, this bit here should look a bit familiar. This is the set type alias that we wrote before. So what we have done here is given two lenses, one lens from S to A and one lens from A to B. We have created the first half of a lens from S to B. Could we write the second half, which is a getter? Well, yes, it's pretty trivial. Same big skeleton, and then you get the A out of the S, then you get the B out of the A, and we have written both the getter and the setter parts of a lens when given two lenses from S to A and one from A to B, so we can compose lenses. given any length from S to A and any length from A to B, we have a free length from S to B. So this is how you compose lenses. It's just taking the code that we just wrote and putting it all together. And now we can create our final lens, the one that will allow us to go straight from an ML service to a classifier name. And now, finally, we get to something that's a bit more pleasing. This is how we do now the whole mess of lines of code that we had before with the copy constructor and everything. And you can modify it, and you can see if I uppercase everything that's in it, then the classifier name is uppercase. And that is pretty much all you need to know about lenses. There's a lot of beautiful theory behind it that I encourage you to dig into, but that's what lenses are about. Lenses are about allowing you to dig arbitrarily deep into nested prototypes and to work with values inside. And the idiomatic way of working with them is to make the smallest possible lenses you can, and then compose them one after the other. So that's the end of the first part of this talk. It would be a good point, a good time to ask questions about lenses, because I'm going to assume that everything we just said is understood before I tackle the rest of this talk. So is it clear to everyone? Apparently so. All right, Prism and optionals then. So the way we have motivated lenses was by trying to modify the classifier name within an ML service. Now let's try to do something slightly different. I don't know if you remember, but in ML service we had the classifier, but we also had the authentication mechanism, which could be either a token or a login composed of user and password. What if we wanted to modify the username part of the authentication login? Well, if we wanted to do that, the first thing we need to do is to write a lens that allows us to go from the ML service to the authentication mechanism. This is a code that we've written twice before, so there's nothing really new here. And then we need somehow to go from our user value, from our login value inside the user. So we don't actually have a login value though, we have an output value. So how do we write that lens that goes from auth to the username part of the login? Well, the answer is that we can't. We can't write that because just the getter part is impossible to write. If we have a login, then it's easy to return the username. It's just pattern match and extract it. But if we have a token, then there is no username to return. We can't possibly write that. So a lens is not going to be the answer to that problem. We need something else. We need something that would allow us to go from an auth to one of the things that constitute it. And that's called a prism. That's because diffract sometimes, I suppose. It's very pedantic, but this is what we call a prism. It looks very, very similar to a lens. The critical important part is this here, which says that given an S, I can return maybe the A that's inside of it. So given a login, given an auth, I might be able to return the username. Might not, might be. So this is the most important difference. Then you have the set, that's slightly different as well. It's called set because it's in the position of get. It's a bit of a weird name, but it allows you to go from a login to an auth. It just allows you to upcast your sum type, yes. And modify is just follow types and implement it. It's not particularly interesting. And we are going to do, as before, create lots of instances of Prism, so let's write some creation helpers. The obvious thing to do, like before, the apply method. And then, because I want these slides to be machine readable, I'm going to do a bit of trickery here. Does everybody know how to pass pattern matches as anonymous functions to empathetic functions? No? Okay, good. I'm going to explain that. So the interesting bit, one interesting bit in Scala is that, first, do I need to explain what a partial function is? Is there anybody who's not familiar with the concept of partial function? Cool. So partial functions are subtypes of function. And functions can be passed to methods that expect functions. So by the Liskov substitution principle, we can take a partial function and put that into a function that expects a function as an argument. And pattern matches in Scala happen to be partial functions. So if we write this method from partial here, which takes a partial function can be lifted. So partial function from A to B are functions that, given an A, might return B. So you can lift them to function that, given an A, will return a sum of B. So this is what we're doing here, and it allows us to write this prism. So the logging prism, which, given an OR, allows us to focus on the logging part, which the set part is just upcasted, and second part, this is what this was all about. It's just we can use a simple pattern match rather than listing all of the possible options. And now that we have a way of getting from an auth to a login, we need a way of getting from a login to a username, but that's a length. And we've written tons of them by now, so we just have username lengths here that works as we expect. How do we compose a login prism? So prism from auth to login, and a username length, which is a length from login to username. We haven't written that composition, so we need to work out how that goes. And so could the composition be implemented as a prism? Let's have a go. If we try to implement that as a prism, we get stuck when we try to write a setter, because in order to set the B inside of the A, we need to get an A. The only way to get an A is from the prism, and the prism doesn't return an A, it returns an option of A. So there's no way to actually write that, because we can't have a function that, given a B, will return an A. We need to have options somewhere in there. So we get stuck, we can't make it work. Well, you can have a go. If you manage to make it work, I'd be terribly interested in seeing how you worked it out. Option.get is not a solution. I hope it's clear for everyone. And so we can't do that composition. So maybe it's the other way around. Maybe prism composed with length give us a length. But we hit exactly the same problem. We have somehow to get the final value here, which is an option of A, I suppose. Yep, option of A. And to get the A outside of the option, which you can't do. You can't do insane code anyway. So it's neither a prism nor a lens. It's got to be another type. Oh, there was a bit of a hint in the name of the section. It was called prism optional, so I'm guessing nobody's going to be very surprised when I say that if you need a hybrid between a lens and a prism, we're going to call that an optional. So I was going to be very snarky here and say, well, yeah, but the fancy optic metaphor kind of breaks down, doesn't work anymore. Ha ha ha, bad naming. But just before I gave this talk, Julien, who actually wrote one of the canonical implementation of objects in Scala, told me, yeah, that's actually not a real name. That's a name I came up with, but the proper name is affine transformation. Affine traversal. So I'm not going to make fun of it because we lost the optics metaphor, but it's even worse, isn't it? Affine traversal. So optional is fine because we get the idea that there's something optional in there, but the names are just all wrong. But the optional here, it's basically the getter part of a lens, of a prism, sorry, and the setter part of a lens. It's just a mix of the two. It allows you to maybe work with a value. And we need the usual creation helpers, not going to waste any time on that slide because we've done that twice before. And now we're going to compose all of them together. So that accounts for a fair amount of these slides, in case you were scared by the amount of slides. I'm not going to go, I wrote them down, every single one of them, so that you can go through them later if you want to. But we are not going to spend much time on them. I'm just going to quickly go through prism with a prism, that composes a prism. Prism with a lens, that composes an optional. Lens with a prism, optional. Optional with optional, optional. Optional with prism, optional. Prism with optional, optional. Optional with lens, optional. Lens with optional, optional. And done. You can stop paying attention again. The one bit that was really interesting, though, that you must notice is when we composed lenses with lenses, gave a lens. When you composed prism with prism, you got a prism. Anything else was an optional. and a thin traversal. Sorry. So we have all the compositions. They have clever names, so initials here, so that compose option with lens, compose lens with prism. And we take all of the lenses and prisms that we wrote in order to go from an ML service to an auth, and from an auth to a login, and then from a login to user name. We compose them all, and we can change our user name just like that. Which this is actually a lot easier than the code would look like if we had to write it in Java because of the optional bit, which would involve a boilerplate. And that's all there is to know about optionals and prisms. The prisms are used to choose a specific value from some type. An optional represents a path when you traverse an AVT that might or might not work out. And they all compose, and somehow you always end up with an optional at some point, and that's it. So that's basically what I want to take away for this evening today. If we stop here, I've shown you what I really had to show you, which was lenses and prisms and optionals solve a problem, which is a problem of modifying data and accessing data within nested ADTs in a way that are actually usable, because in Scala it really isn't. It is really, really annoying to have to use a copy constructor all over the place. Do you have any questions at this stage? Is it just really very clear, or so obscure that you don't even dare ask a question?
Yes.
Okay, let's pretend it's very clear. That's going to make it easier for me. Now, I know I'm supposed to be finished at 8, but I started about 10 minutes late, so I'm going to at least show you the libraries that we have in the Scala ecosystem that allow you to work with optics. So the first one, Scala Z. Scala Z has lenses. They're called lensu. Not quite sure why. Just a thing. And they're pretty crappy, really. They're basically what we've done so far, but that's all they have. They have lenses. They do not have prisms. They do not have optionals, just lenses. And you have to write all this code by hand. So it's in Scala Z. If you have Scala Z in your class path, you might want to use that. But it's, of all the implementation I've seen in the Scala ecosystem, it's by far the worst. It's worse than what we've done tonight. So if you can not use them, please do. And then you use them pretty much the same way as what we've done so far. You just call set with the values. It's not carried, but it's a minor difference. So yeah, Scala Z, don't do it. Shapeless. Shapeless, on the other hand, is absolutely gorgeous. This is all the code that we wrote. This is what Scala Z, Shapeless. Scala Z. This is absolutely beautiful. It's absolutely magical. It just works things out. You say, well, I want something that's a name, the classifier in my ML service, and work it out. So Shapeless will work it out. Yes?
I don't think it works very well with your IDE, because all of this is like white macro.
Okay, my IDE is Emacs, so I don't have that problem. But yeah, apparently that doesn't actually work out so well with IntelliJ. This is not much of a surprise. Nothing really works out very well with IntelliJ anyway. Sorry. No, I love IntelliJ for Java. It's a great tool. And Shapeless here, it's going to work the whole thing out for you. It's pretty amazing when it works. When it doesn't work, when you're not doing exactly what it expects, then it's going to be a bit nasty. It's going to say something like, could not find implicit of type blah, blah, blah. You have no idea what it's talking about. Debugging that is a nightmare. It takes 15 minutes to compile, but when it does work, it's absolutely, I mean, this is absolutely gorgeous. This is absolutely amazing. I'm joking about the Shapeless thing and all, but the fact that this can work is absolutely incredible. And then the use-site API is, the use-site API is basically the same as ours. There's just one weirdness in the Shapeless implementation. So, because they have lenses and prisms, but not optionals. But weirdly, what they call prisms, we call optionals. So what they do have is lenses and optionals, and not prisms. I don't know why. But it's a mystery to the ages why they didn't use the normal standard names. But you have everything you need in Shapeless, provided all you want to do is what I have shown you in this presentation. And then we get to Monocle, which, well, that's a bit intimidating because the creator of Monocle is in the back of the room, and I hope I'm not going to say anything wrong here. But Monocle is the most used, most well-known implementation of lenses in Scala. It's slightly more verbose than Shapeless. Shapeless is that. Beautiful when it works. Monocle is that, slightly more verbose. Now, I know that the next version of Monocle is going to be much, much better than that. Julien showed me, I didn't have time to integrate modification to the slides, but the upcoming version is approaching that, or almost identical to that, pretty much. Come again?
It's getting closer.
It's getting closer, right. So it's going to get much better. So the syntax is still a bit heavy-handed here. You still have to guide it quite a bit, but it works out. And more importantly, we have talked about prisms, lenses, and optionals, but Monocle has so much more than that. A lot of things that I don't want to talk about tonight because it would require me to introduce lots of abstractions that I don't want to talk about. We have another -3 minutes, so we're not going to be able to do that tonight. But Monocle is really the best possible implementation of optics in Scala that you can put on your class staff at the moment. It was also pointed out not too long ago, before I had the time to lay the slides, that there's another one that's quite famous at the moment called Quick Lens by Adam Worski of Software Mirror fame. It's apparently very good, a lot less boilerplatey than other implementations, but not that principled, and you get into odd edge cases. So really, Monocle is, as far as I can tell, the best solution that exists on the market at the moment for Scala. Just what I said. And in conclusion, optics are useful enough that we have 3 different popular implementations in libraries that everybody has probably heard of. Scala Z because it's Tony Morris, and the other ones because they're actually good. And if you need optics, you go for Monocle. It's the best implementation I know of. I like to crap on Scala Z. It's a beautiful technology. It's easy to make fun of. I apologize for the people who, they're probably maintainers of Scala Z here. I love the work you do. It's just too easy to make fun of it. And I need to get a few laughs out of you to know that you're participating. And I'm probably going to be stopped at this point. No, can I? This will take another 15 minutes. Is that all right?
Yeah, yes,
Okay, all right, let's go. So now what I'm going to do is to give you a concrete use case of optics that do not involve actual ADTs, because you can use that for something else than ADTs. What I'm going to do is I'm going to create a type that represents a configuration value. It's really simplified as much as I could simplify it. A configuration value is either a section, which is basically, yeah, I should have shown that first. So this is my configuration. That's going to end up breaking. That's twice. That's going to end up breaking. So I want to be able to pass this configuration file. It's basically JSON, and I want to store that into this type, which is either a section, which is a map of name to other configuration values, or a configuration value, which is a field, which is basically the value. So this JSON file would be mapped to this actual value here. See, I've even aligned it so that you can make sense of it when I switch back and forth. It's really neat. Right, so we have our configuration value, and we'd like to have a good way of updating values nested inside of it. Something, DSLs there all the rage. We would like to have a nice DSL to update that. And the obvious solution, because we've been talking about optics for 45 minutes now, the obvious solution is going to be optics, at least tonight. So we need a prism on a section. A prism on a section is something that's going to allow you to go from a config to a config section. So config is some type, right? It's either a section or a field. So we want to be able to go from a section to, from a config to a section, and from a config to a field. I'm sorry, I didn't actually think I'd get to this point, so I haven't rehearsed that as much as I could have. So this might be slightly less smooth than it was before. But right, so we've done the prism for section, allows us to go from config to a section. The prism for a field allows us to go from a config to a field. And we also need to get access to a given field from a section. And the section is, well, what's inside of a section? It's a map. So that's not actually an ADT. Well, we can still write an optional for that, because the map is basically an optional. It allows you, given a string, to go maybe, to get maybe the associated value. It might not be an associated value, so you get a none. And if there's an associated value, then you get that in a sum. So, yeah, okay, I'll speed up. Right, so this is how you implement that. And then we create something that's called config path, which allows us to work with our configuration value. So this, I'm a bit lost in these slides, to be honest. I haven't looked at them. I really didn't think I'd get that far. So, how does that work again? Well, let's work it out together. If you have any idea what's going on in here, help me out. Right, so the config path, the point of that config path thing is to allow you to get from a section to however deep you want by writing combinations of as fields and as sections, and or asking for a child. So, not very interesting. And this is how we'd write the config path for a classified name in the configuration that I wrote here. Right, so I want to go from my config to the classified name, right? And this would be how you'd express that with config path, which is quite neat. We go from the identity to classified to name, and then we want that as a field. It works. It's not great. We can make it better. And one way of making it better is using dynamic. Does anybody know what dynamic is? There's a good 3 or 4 people. I'm going to explain it. It's going to feel really dirty. It's not. It's very well thought out. It's type safe. It's everything you want it to be, but it's not going to feel that way. It feels like you're doing Groovy again. So if I have the subject upcase, that extends dynamic. What's going to happen is that whenever I access a field of upcase that is not defined, then it's going to turn that into an argument to the method select dynamic. So here, I call bar on upcase. Upcase doesn't have a bar method, so it's going to pass bar to select dynamic, which returns bar as an uppercase, and upcase.bar returns bar as an uppercase string. It looks weird. It's great. It's very obscure. It's really, really great. It's completely safe. It doesn't feel that way, but believe me, it is. And it allows us to rewrite our child before as select dynamic here. Exactly the same code, except now we call it select dynamic and public path is dynamic. And now we can write this, which is quite a bit nicer, isn't it? Classifier.name.asField. We explore it exactly as we would write with the objects we've done previously.
This is the code generation that you mentioned before?
No, the code generation was shapeless.
Oh.
And this bit here I'm still not entirely happy with, so we're just going to call it root. And now we can write root.classifier.name.asField to, for any configuration object, get the name of the classifier as a field if it exists. And then we can modify it exactly like want to. So I want to set it to news20, and that works out. Right, so that last bit was a bit, didn't work out so well. I'm really sorry, I didn't think I'd get to present that. Optics can be used to explore more than just simple ADTs. And if you want a really neat, really useful implementation of what I've just shown you with config path, you have JSON path with Cersei, which is pretty amazing, really. I didn't know about it, I've not actually used it, but when I actually discovered it, it's really well written. Travis Brown, he writes beautiful code. Have a look, it's absolutely gorgeous code, it's beautiful, and you want to know how that works. To wrap things up, optics, they're really, really great to work with nested data. Sorry. You do not need to understand the theory that goes behind it. Technically they're called pro-functor optics. But the theory is absolutely beautiful. It's absolutely gorgeous. There's a brilliant talk by Simon Clayton-Jones in which he explains the concept and the theory behind lenses. It's absolutely amazing. It's incredible. So I encourage you to watch it. But you don't need to know these things to use optics. You don't need to know the complexity. You just need to know what you use them for. And existing libraries such as Shapeless and Monocle make them almost painless. So please, if you ever need to do something like that, consider Monocle. It's a great tool for that job. Slides are already available. I'll post them on the meetup afterwards, so if you want to have a read. You can follow me on Twitter. I work for, as I said before. And do we have any questions? That's never a good sign. No question whatsoever. Not even about that last bit that really didn't work out so well. You understood all of that, because I didn't. Okay, great. Well, thank you very much.